Okay, so today we're going to talk about um, non-parametric tests. So let's get into this. Most tests that we do in statistics, we know the distribution of the dependent variable, and the test statistics we use depend on that distribution. So no, the normal distribution is a primary distribution we work with, and most of the test statistics we use assume normality. So we're looking at the outcome variable or the dependent variable. And in all cases, you're always looking, you only care about the distribution of the dependent variable. As far as the other variables, it's important to code them so that you can make sense when you're trying to assess their effects on the dependent variable. But really what we're doing is we're interested in the distribution of our dependent variable. And in many cases, we can't assume normality, but when we can't assume normality, this becomes problematic. And one of the most common ways people deal with this is to do a transformation of the dependent variable. One of the most common transformations is this not natural log transformation. So in other words, they just take the natural log of the variable. So if whatever your score is, take its natural log and that's your score. And what that does is it helps to hasten the transition to normality or the convergence to normality. But it also results in really hard interpretations because now we're saying, what's the effect of our predictor on our outcome? It has an effect on the natural log of whatever, so the natural log depression or something like that, and that doesn't make sense for most people. So it's okay, but I don't think it's a very good way to deal with your data, especially if you are interested in having people understand what you're doing. We can also use non-parametric tests. So a non-parametric test is a test that does not depend on the assumption of normality. I'll be getting much more into that now. So in terms of a test that compares two independent samples, when we can assume normality, we use the independent samples t-test. I mean, you can also use ANOVA, but when we have two samples, why not use the independent samples t-test? That test assumes that the dependent variable is normally distributed at each level of the independent variable. So if we're comparing, say, males and females, we're assuming that the whatever our dependent variable is, let's say we're looking at a comparison between males and females in depression, we'd assume that depression is normally distributed for males and for females. Okay. Also assumes independent observations and assumes equality of variance for both groups. Again, we know that we can relax that and there are tests that will allow us to relax the equality of variance assumption, but really the main problem is this violation of the normality assumption. When we have that, we cannot use or you can, but it's not going to be as good if you use the independent samples t-test. And again, people can normally, can do a transformation if they wish, but that again makes it difficult for us to interpret. So today we're going to talk about one test that we can use in this situation, and that's a not well, people like to say a non-parametric equivalent. I don't know if I italicized equivalent, but it's a non-parametric test when you have two independent samples, but they are not normally distributed. So I don't know if I really want to say equivalent, but since most people say it, I'll say equivalent. So it's not exactly, oh, this is the counterpart for the independent samples t-test when you have non-parametric data. So again, we've talked about population parameters, right? A non-parametric test does not assume a known distribution. And generally it means it doesn't assume normality, right? But we don't know the distribution. That's what a non-parametric test does. Okay. All right, so let's look at how this is done. It's interesting though, and I mentioned this in my newer textbook, which you may have if you're in my other class. I talk about these non-parametric tests, and most of the people assume that these tests use the median. They're tests of the median, but they're not. They're tests of rankings. They're tests of rankings. Okay. So that's what we have to do with it. We're comparing rankings. So let's go over what the process looks like. Again, you don't need to do this by hand, but you need to understand what's going on. Okay. First thing, we have data. Like let's say we have depression and we're comparing depression in two separate groups. In fact, that's what we do here in this test. See depression score. This is I'm just going to jump ahead just to give you context. This is an example of a study where an investigator was looking at the depressant effects of recreational drug, right? So this is fictional, tested 20 clubbers. 10 were given an ecstasy tablet to take on Saturday night. 10 were allowed to drink alcohol. Okay, so but no ecstasy tablets. So you get 10 and 10. So you want to make a comparison between the two groups. And they were using the level of depression measured using the Beck Depression Inventory the day after on Sunday and then the day after on Wednesday. So we have two sets of data, Wednesday and Sunday. So these are your scores, your depression scores up here, right? For Wednesday, and these are your depression scores for Sunday. So what we do here is we start by putting all the data together, right? So these are the scores from lowest to highest, right? Then we assign them ranks. So notice this is potential ranks and actual ranks. So for instance, you have 3, 5, 6, 6, 7, 8, 9, 10, right? So 3 would be ranked the lowest, number 1. 6 would be number 2. Then you have, I'm sorry, 5 would be it's a 5. 5 would be number 2. Then you have these two 6s, so that would be 3 and 4, right? That's how they'd be ranked. I mean, even though they're both equal, then we go here, 5, 6, 7, 8, etc. When you have tied ranks, like these two ranks, these scores are tied, right? 6, 6. What you do is you take the average of the rankings. So you have 3 plus 4 is 7 divided by 2, and they're each given 3.5. So that's exactly how this is done. This is how we calculate the ranks, right? So again, you do that for everything. So you start here, 6, 7, 8, 9, 10, blah, 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 11, 16, and then 36, this is 35, 35, and 35. So that would be 16, 17, and 18. So we take the average of those three, which is 17, right? 16 plus 17 plus 18 divided by 3 is 17. So these are the actual ranks. So that we get the actual ranks for all the data. Then we divide the rankings, we divide them based on the grouping. In this case, the grouping was ecstasy versus alcohol, right? So we divide them. So you see this is E for ecstasy, A for alcohol. Then we sum up the ranks. We add the ranks together. So 1 plus 2 plus 3.5 plus 3.5 for alcohol, right? We get them, and then we'll get a sum of ranks for alcohol. In this case, it was 59, and then we get a sum of ranks for ecstasy. Same thing happens here, right? The scores for Sunday, we do exactly, there were a lot of tied scores here, 15, 15, 15, 16, 16, 16. So we get these averages, right? Then we add them together again, and we get the sum of the ranks for ecstasy and the sum of the ranks for alcohol. Okay, so that's what the ranking is. We're dealing with rankings. We're not dealing with medians. We're dealing with rankings. Okay, and so you'll see sometimes that people talk about medians. The medians do apply sometime, but in most cases they don't apply. So then in that case we use rankings. All right. But this is how the test works anyway. Test is known as the Wilcoxon test. The Wilcoxon, where is it? There's some rank test because there's two different tests. There's a rank sum test and the sum rank test, and they just drive me nuts. But because it's hard to remember which is which. But so this is the sum of the ranks, Wilcoxon sum rank test. Okay, so let's go through this a little bit more here. So we did that. We add up the ranks of the two groups. Our test statistic is the value of the first summed rank. So this has always confused me, which is the first, because I can put them any one, right? I can do alcohol first. Like if I'm entering data, I could do my alcohol first as level 0, and then level one could be S to C, so then zero would come first, right? Or I can do the opposite ways, but it doesn't matter really technically. So when we have equal group sizes, we use the ranking of the first group, and then unequal sizes, it's the sum of the ranks of the group that contains the least amount of people. Sometimes we'll have situations where you have a smaller amount of people in one group versus the other. But we'll see that when we do when we run the analysis. So here's our example. So there's two ways we assess this result for significance once we have the W. This is our Wilcoxon value, right? Once we have the W, one of the things we can do is just use it alone and assess the value for significance. And another way to do it would be to convert it into a normally distributed random variable, standardizing it and getting a Z value and then just using a normal table. And that works because of the central limit theorem. So the central limit theorem states that once we transform a variable, and as long as it has what's called I just have to give this qualifier, as long as it has a finite mean and a finite variance, you can use, with a larger sample size, the distribution of that variable will converge to normality. Okay, and if you're interested in that, I have a proof. I actually proved the central limit theorem. You can watch that video if you want to torture yourself. Okay, but to do that, we need to standardize our variable. So let's take a look at this. So this is an example of how we standardize our variable. We need some sort of a mean and we need a standard error, right? So this is our standardization. To get our mean, we get the mean of this W. So that's our Wilcoxon, our test statistic. It's the number of individuals in group one. Again, it doesn't matter which is which, times the number of individuals in group one plus the number of individuals in group two plus one, divide that by two. So that's our average. And then our standard error is kind of a play on this, right? It's a play on this value here. Our general Z equation would be X, whatever our X is. In this case, it'll be our W minus the mean divided by the standard error. So let's go ahead and do that here. So we make this conversion. We have our W, which is our Wilcoxon score, which was the first of the two groups. In this case, and I'll show you this one. I'm going to run this for you. The first value was 119.5. And we subtract 105 from that because that's the average. That's our average, right? I think, did I not calculate that? It's our average using this equation here. It's our average, and we get our standard error for the W's is 13.23. We get a value of minus 1.10. This is a Z value of 1.10. So we've kind of already know that this isn't going to be good, right? Because we know Z value, especially if we're doing a two-tail test with an alpha of 0.05, we know our critical value would be plus or minus 1.96. Okay. So this is telling us that the value on Sunday does not statistically differ from the mean, what we'd expect by chance alone. And then on Wednesdays, though, we have, excuse me, on Wednesdays, we do have a significant result. Again, we take the value of the first W, right? Summation of all the rankings from the first group. It's 151 minus that mean divided by our standard error of the mean. And we get a negative value of, well, actually, this should be positive. I don't know why I have negative there. I know why. Okay. And in the last, when I first wrote this, I didn't use 119. I used the other value. So 119 minus 105 is 110. So these are positive values. Okay. So in this case, 3.48 is greater than 1.96. So we do have a significant value. Okay. So that's just showing you how this works. But the Wilcoxon ranked sum test is often reported as the Mann-Whitney U. In fact, you can actually call it the Mann-Whitney U test, or you can call it the So it's rank sum, not sum rank. I tell you, I get these confused all the time. Again, so I mean, you can just call it the Wilcoxon and Mann-Whitney U task. So they're mathematically similar, but you don't. Unfortunately, I was looking to see if I could get that calculation in SAS, and I don't get it. So we're not going to get it. So you'd have to calculate that by hand. And it's not really a hard calculation. It's the sample size of group one times the sample size of group two plus the sample size of group one times group one plus one over two. And you subtract from that the sum of the ranks of group one, whatever that sum of the ranks is. So let's actually do that here. Note that it doesn't matter which group is selected as group one. That's absolutely true. So for Sunday, so the Mann-Whitney U for Sunday is 10 times 10, right? There's 10 in each group. 10 times 11 over 2 minus our group value was 119.5. So we get 35.5. And then for Wednesday, I get 4, right? So I get 4 because our first group sum was 151. Okay. In this case, I'll just use SAS for the p-values. All right, so that's what we need to know. So this isn't the same as something that we've seen before. The key with all these non-parametric tests is the use of rankings, right? You use rankings in order to conduct your analysis, which is a little different from what we've done before. But it would be torture to have you do that. So I'm not by hand. So we're going to go straight to SAS to do this. So we're going to use this procedure called n-pairs of non-parametric for one way. Well, this is basically like a one-way test. There's one independent variable. We're going to ask for the Wilcoxon values. And here, this is interesting. I was looking up the code here, and in one example, with a small sample size, people set this correction to equal no. What is this correction? When we convert something from a non-normal to a normal, like we do with the z-test, we have to do a continuity correction because we're not dealing with a continuous variable. We're dealing with a discrete variable. Then we want to treat it like a continuous variable, right? When we do the z-test. But this was a really small sample size, so the continuity correction was set to no. I would recommend, and what I was trying to do here was replicate what I had in the original textbook that I used. So I did the non-continuity correction, although I would recommend doing it all the time anyway, because you're converting something from non-normal to normal. I think I'm going to put this in here twice. I don't probably need that again because it's already here. Yeah. All right. So we also talk about what our predictor variable is. In this case, our predictor variable is drug, whether it's ecstasy or it's a alcohol. So it's our class statement is used to create dummy variables, right? So this is going to be our dummy variables variable that's 1, 0, or with 2 levels, right? Some kind of comparison group. The variables we're looking at are the Beck depression inventory score on Sunday and the Beck depression inventory score on Wednesday. And then we're going to do this thing called an exact test. An exact test is used when you cannot, for some reason, do normality. Like this has a really, really small sample size. So we'll use an exact test. This is like the Fisher exact test, if I think about it. This was like you calculate probabilities using the binomial. If you remember doing the binomial, we'd actually calculate the probability for each level, right? Versus when we use the z-test, we have the beautiful normal distribution and all the probabilities available there. Okay, so we'll do the exact test. So we're going to run this, okay, in a moment. Then we're going to report our results in terms of, well, whether or not we had statistical significance, but we'll also use an effect size. An effect size is a way to standardize our results so we can make comparisons. Like what is the effect here of the difference between these two groups? And we can use the R in this case. That's a correlation coefficient. We take our Z value and divide it by the square root of the sample size. So this is the Z score we get. Like for instance, in this case, we had a Z value for Sunday of, I should be 1. Why did I do that minus again? So it's just 110. Score was 1, 10 divided by square root of 20, and we get 0.248. And if we look at these heuristics here, for R, if it's less than or equal to zero point 0.3, it's considered small. So this would be considered a small effect, okay? And then for the second one, for Sunday, we had a larger effect, right? So 3.48 over square root of 20, we got 0.778, and that is a large effect, is greater than 0.5. Okay, so let's go ahead and run this analysis, then we'll talk about the output. So we're going to go back into SAS Studio. So I gave you all the code, so you can just go ahead and run it. So I don't need this second Wilcoxon here. Actually, let's start here. All right, so here's our code, just as I discussed. So let's go ahead, and I have a data set loaded in your module for today. I have two data sets loaded, and you probably already have access to one of them. But I have two data sets loaded for day. One is drug.sav. Again, so this is a SPSS data set. So don't try to open it on your computer, just save it somewhere. Like this is in my download. That if I download it, that's good enough. I don't need any more than that. Then I can upload it onto SAS, right? Upload into SAS. And what I did was I uploaded it into my personal area here, right? So it says drug.sav. Then once you do that, you click import data and it'll import it into SAS itself, and it created a SAS data set, right? drug.sas7bdat. Okay, so that's my new data set that I'm working with, okay? And I already linked this to my library when we started this course, so I don't have to do that again. All right, so this is data is equal to mvstats.drugs. This is the library, and it's called drug, right? And then my classification variable just so happens to be drug as well. So, but let's take a look at this just to make sure everything's good. Let's take a look at this. So I ran a proc contents. Proc contents just tells me what the variables are in my data set and gives me other information, like your 20 observations, etc. So we see I have drug. They're all numeric. They're not character variables. I don't have to do any conversion, but I can work with those too. We have drug, type of drug, and we have the Beck depression inventory for Sunday and for Wednesday. So I know, as long as I know the names of the variables, I'm in good shape. Okay, and then I can go ahead and run them. But first, I want to make sure, we're going to run it anyway, but I'd like to make sure that they are not normally distributed. So I can do this proc univariate. I'm going to just copy it since I already did it for something else there we'll be using in a second. Let's do this here, put it right here, Control V, and our data set here is drug. I love that this works like that, drug, and my variable was those two variables, which are here actually, Sunday BDI and Wednesday BDI. I'm just going to copy those and paste them here, Control V. There they are. And so I'm doing a proc univariate. If you recall, when we look at descriptive statistics, this will give me a view of my data, but I'm also asking it to give me the normality test and the plot, a histogram, right? A histogram to allow me to see, and with a superimposed normal distribution on it, to see, and a QQ plot, quantile plot, so I can actually investigate whether or not we have normality. So I'm going to look at that. I'm going to run that. And actually, I'm going to do one more thing before I look at that. I forgot to do one more thing. I'm going to see if I can do this here. Can I do class? Yes. I'm going to do classify them by drug. All right. So I can get two separate ones. So we need them for each level of drug. All right. So this is drug is equal to 1. So this is Sunday. Drug is equal to 1, whatever that is in this case here. We'll take a look at that. All right. We're really interested. I'm not interested in a lot of this stuff. What I'm interested here is in test for normality, so we can see not normal. So we have these different tests, like the Kolmogorov, Smirnov, Shapiro-Wilks test. Those are good tests. They look for whether or not we have, well, our null hypothesis basically is that they're normal and otherwise they're not normal, and we find that these p-values are small, so we reject the null hypothesis. And we can also take a look at both. And for this is for drug equals 2, same thing. Well, here it is. Well, here drug equals 2, it seems like we don't fail the assumption of normality, but because one of them we did, we're just going to go ahead and treat this as non-normal because I need them both to be normal. I look at Sunday for drug 1 and for drug 2. Well, I don't, I mean, that does not look normal, right? So it's funny, even though we're told that they are normal. This is for what? This is for, yeah, for Sunday and then for Wednesday. What Wednesday? Was that Wednesday and Sunday? Well, give me one plot here for drug equals one Sunday BDI. Didn't give me one for Wednesday BDI. There it is, Wednesday. Okay, this one, I mean, yeah, they don't look normal to me, even though I suppose with the test you can come up with these solutions. But okay, so yeah, that's what we get. All right. It's lots of data to look at. So I think I feel pretty good that we don't have normally distributed data so that we can go ahead and use. So this didn't give me the line for the QQ plot. But usually oh, because we separated them. So if we had a normally distributed value, our points would fall on a line that's like going across the diagonal here. And they're not, it looks like there's some divergence. All right. So what I do now, I feel good that I feel good that I can use the non-parametric test. All right, so that's done. So I'm going to look at the non-parametric test. I'm still going to go with this no corrections because that's the way it was done initially. And I'm going to go ahead and run this analysis. And here's my output. So I have two groups this is for Sunday. Group 1 is 119.5. Group 2, these are the sum of the ranks. We have 90.5. So that's the mean score on the BDI. I think this could be the mean ranking, actually. So here we have our ranking. So it's 19119. That's our first one. So that's our test statistics. That's our test statistic W. It's the first group. Our z-score, we already calculated that. It was 1.10. And here's our probability. So this is the probability of a value greater than z. On a one-tail, we get 0.1346. If we did a two-tail, which is what we did here, we double this value, because remember, two-tail, you double the probability for the one-tail, we get 0.2692. Okay. And here's our exact test probability. Our exact test probability is also above any value we would use as a criterion. Usually people use 0.05, 0.10, 0.01. Well, these are all larger, so we would fail to reject the null hypothesis that there's a difference in ranks between the two groups on Sunday, right? The alcohol versus the ecstasy group. This is also a test that is more for an ANOVA when you have more than two groups, but it's okay to use it with two groups, the Kruskal-Wallis test. It's like an ANOVA equivalent when you have non-parametrics. You can see the medians here. You can see they are different, right? Between the two groups, but they're not statistically different. There's a lot of overlap here between these interquartile ranges. That's these gray areas. All right, let's look at Wednesday BDI. So now again, our sum of rankings, we have 151 for the first group and 59 for the second group. And our test statistic is the sum of the ranks of the first group. Our z-value, which we calculated by hand too, I showed you that, has a very small p-value, either one or two tail. So this is statistically significant. An exact test is also has a small p-value. So it is statistically significant. Okay. You can see that we have this separation and even the interquartile range, we have very little in common, but nothing in common between the two here. All right, so let's go back to our output. All right. So what did we learn here? Wait, let me go back here. So I showed you how we calculated. I think I showed you. Yes, I did show you how we calculated the U value, right? Right. So I showed you how we calculated the U value. So because we don't get it, so we're just going to calculate it by hand, which isn't that hard a calculation, knowing what we know, right? And I think SPSS gives it to you from what I remember, but SAS I didn't see it unless, again, I'm relatively new working with SAS, but I did a lot of Googling to find a code for it, and I didn't come up with any. So let's go ahead and look at these results. So I wrote this up. Depression levels in S to C users. Median is 17.5, did not significantly different from alcohol users. So I just give you the medians. The day after the drugs, well, you report medians anyway if something is not normally distributed. Otherwise, I'd report the mean. The day after the drugs were taken, W was 119.5, or z-value was 1.10, and our R values wouldn't be negative, right? Was 0.25. However, Wednesday S to C users were significantly more depressed than alcohol users. Okay. And we show the statistically significant Z value. Just get rid of all these negative signs. Okay. So that's if I want to report the Wilcoxon test. If instead I'm going to report the Mann-Whitney test, but now we know that these are basically saying the same thing, right? Depression levels in S. So basically it's the same, right? Depression levels in S to C users did not differ significantly from alcohol users, and I give our medians again. The day after the drug was used, and I report the Mann-Whitney U, I report the Z value, and everything else. However, on Wednesday, S to C users were significantly more depressed than the alcohol users, right? So again, I report all these results here. Okay. So it's kind of cool. It's something different, right? Uh, a lot of times, like when I teach intro stats, we have a lot to cover. Generally, I focus mainly on the normality stuff because students are having enough difficulty just dealing with just normally and distributed data that are continuous and everything. So to introduce something that's more complicated, especially where there's issues, like there's issues here in terms of whether people should assume that the test of median versus a test of ranks. It gets complicated if I start explaining everything to students. So generally we teach them normally distributed data, especially when we're talking to students who are not studying statistics, or that's my love is statistics. So if they're not studying statistics or math majors or some kind of really hardcore scientist or something, then of course if they were, then we go and delve into much deeper level. Okay, so let's do another one as an example. Question is, do smokers differ from non-smokers on the number of pure smoking? So we're going to use the My First data set to test whether the two groups differ on the number of pure smoking. So probably not going to be normal. I mean, you think about it's a count variable, so it's a discrete variable. All right, so first we'll start by testing pure smoking for normality, and this is the code for testing pure smoking for normality. And again, I saved it in my library. You can create your own library. You want compare it, call it MB stats, and then The data set is called my first data set, which you download, and you probably already have now. And then we'll run this code and see what happens. Okay, let's go back to SAS Studio. Here we are. All right, so I set everything up. The proc univariate data equals mvstats dot my first data set. And again, I'm going to test for normality. Now that's the variable I'm looking at. It's my classification variable. Let's try this again. All right, here we go. So we have 319 cases. This is some interesting stuff under not having any peers, not smoking, under not smoking. Here's our normality test. So we reject the assumption of normality in all these cases, right? P-values are pretty small. Again, of course, you can look at the data. You'll see that, this is what they look like because this is just the number of pure smoking. So you have these like these masses of where the individuals are. And then for the group that had cigarette smoking, test for normality. Yep, cigarette smoking is equal to 1. We also fail all those based on the test. Then we can take a look at you see the differences. They also don't look normal. So that makes sense. And what's this one for? Oh, and then this is for, must be one was for Sunday and one was for Wednesday. And we got 0 and 1 here. Failing of the normality test here. She looks terribly weird, right? All right. Yeah. So we did that for pure smoking. Oh, it was only I'm sorry, that's Sunday and Wednesday. It was just pure smoking, right? So that's it. All right, so we did the univariate test, the proc univariate to check to see if we have normally distributed data at each level of binary smoking, and we don't. We cannot assume that. So we are right to use this test. And notice here that under the continuity correction, I pressed yes. This is a large data set. And like I said, you should always do that anyway, because we are treating something that's discrete as continuous. So we should do this correction, which either adds or subtracts 0.5 to the score, right? To the z-score, depending on, whether we have negative or positive value. So let's go here. We have a procedure again. We're using the Wilcoxon. I don't need to report that twice. And our classification variable is binary smoking. We're looking at pure smoking. We're also going to do that exact test. I don't really need it. It's a large data set, but I'm just going to do it anyway. So I hit run. All right, so it's only one result here because unlike the last analysis where we had 2 variables, we're only looking at 1 variable here. We have 70 individuals in the first group, so this is not equal sample sizes. And this is also our first group, but it would be the group that has the smallest, the score of the group that has the smallest sample size, which just so happens to be the first group here. So our sum of our scores is 22029. So that's our test statistic. Our t-value, right? Our t-value is 10.246. And if the probability of value this large or larger, given the null hypothesis is true, is less than 0.0001. And we don't really need the exact test here because we were dealing with a large sample size. So this is pretty much all we need. Okay. And if we wanted the Mann-Whitney, we'd have to calculate that by hand here. And I don't need this Kruskal-Wallis test either. We can take a look at these. You see these differences are pretty big. One of the things, because we have a large sample size, the larger the sample size, the more likely any difference is going to be considered statistically significant. Okay, so that's something that's very, very important to note. That's why you calculate things like the effect sizes, right? So you do the effect size so you can know whether or not we have a large effect or not. Um, yeah, so you'd want to do that as well. Okay. But again, having a large sample size will make anything look statistically significant. And the difference here is, it's somewhere, the median is somewhere like in medians right here. It's like 350 versus, less than 200 things. That's a substantial difference. Okay, and the rankings are a pretty big difference too in the rankings. So again, we're dealing with the rankings here. All right, so that's how you'd run this. And then your next assignment actually is, which will be due after get back from spring break. You're going to use this My First Data Set test whether individuals drinking alcohol on at least one day in the past 30 days differ on the number of peers smoking from individuals who do not drink alcohol in the past 30 days. Write up your results as I showed you in class. However, this is an interesting problem because the alcohol variable is not set up to be binary, right? So you're going to have to set it up to be binary. So let's actually take a look at the alcohol variable itself. So let's go back into our hot tub time machine here to find our code sheet. See where our code sheet is. I think I had it in the last class. Let me see. I think I had it in week 8 or somewhere. Let me see. I did have the code sheet there. No, week 7 maybe. Let's see where I had it. Oh, I might have it here. Data sets. My first data set. Do I have the code sheet here? No. Well, I got to find that code sheet. So I just want you to see what that I mean, I could run it for you anyway. So actually, I could just do that because I know what it is. But somewhere in here, somewhere in this class, we have the code sheet. It actually might be in your assignments, like an assignment 1 or something like that. It might be in your assignments, but you do have the code sheet, so it'll tell you exactly what the levels are. But I know most people don't drink alcohol, so even though a lot of people do in high school, but most of them don't drink alcohol. So I would assume that the lowest level is the value where most people don't drink alcohol. But I would need you to confirm that looking at the code sheet. Let me try one more thing to see if I have the code sheet in here. Let's see, this is download. Let's go to actually here. Syllabus. Our downloads. So the C's. So this would actually be helpful. So I apologize for taking long to do this, but I think it would be very helpful to find it. Let's try week. I don't think it was in week 1. Maybe let's see, week 1. Code sheet, not that code sheet. We don't want the C's code sheet. Try week 2. Code, here it is. Okay, perfect. All right, let's look at the alcohol variable. So 0 days is equal to 1. 1 to 2 days is equal to 2, etc. Okay, so it ranges from 1 to 7, but that's 0 days versus pretty much everything else. Okay, so that's going to help us in our coding. All right, so let's go back to coding because I love coding variables. So this is how you're going to do that. Let's call this assignment 3. Make sure you're watching this because people are going to ask me, I don't know how to do that. Well, I'm showing you right now how to do it. Okay. So first of all, my data set is my MV stats dot my first data set. So I'm going to just create a new data set. Data. And I'm going to call this data. What do we want to call it? We're going to stick it in the MV stats library, and I'll call it assign 3. 3. Okay. All right, so this is how we start. So this is going to be my new data file called assign3. Notice that I have the underscore there to not cause any confusion. I'm going to set it to an existing data set in MV stats, my first data set. So now if I did nothing else and I type the run command, it will just copy that data set. Now you can do anything you want. I mean, one thing you could do, since we're only using two variables here, right? By alcohol use and alcohol use and pure smoking, I could just keep those two variables. So I might do a keep statement, right? And just have those two variables in the data set. So one is pure smoking, and the other is, what did we call alcohol? Let's go back to the code sheet. Code sheet, I think it's just called alcohol. Alcohol. All right, let's go here. Alcohol. Okay. So I'm just going to keep those two. So if I just run this now, I'll create a new, I'm going to do this just to make sure I didn't mess up in some way, put the wrong variable names in here. This will create a new data set that just has two variables in it, pure smoking and alcohol use, right? All right, go back here and if alcohol, well, we're going to just I'm just going to recode it into the same variable. So if alcohol, well, equals 1. But let me just, before I do this, let me just make sure that these are quoted from 1 on like their set. I just want to make sure before I do. So we have this data set called MV stats assignment 3. So let me just, for a second, I'm just going to run something really, really quick because I just want to make sure. I'm just going to do a print. And this may not be the best way to do it, but I mean, I want to take a look just to make sure there aren't any zeros. Proc print data equals MV stats dot assignment 3. There it is. And I'm going to print the first 10 observations. I don't really need all observations. Maybe I'll do, actually, let me do like 100 because there's 300 something. So this will actually make sure there's no zeros in it. Okay. So let's take a look at the first 100 observations and just take a quick look to see if there are any zeros in there for alcohol. So it looks like 1 is the lowest level. Yeah, there are no zeros. I just wanted to make sure so that when I'm recoding, I don't mess up. And we do have missing values, which is important too. All right, cool. So if alcohol equals, I think I just have to do this. Let me see. If alcohol equals this, I may have to surround this. So if it's missing, no, that's okay. Actually, if alcohol equals 1, then alcohol equals 0. So I'm recoding this, and I'm pretty sure that I have to stick quotation mark. Again, I'm kind of new to this coding. Again, it's been, 15 or so years since I coded SAS. So if I make a mistake, it'll tell me and I'll know to correct it. So kind of working off of memory and what I've learned recently. So we're going to recode 1 to 0. So we'll have did not use alcohol in the last 30 days. Else, if, well, I could just say else it is equal to 1, but then that would mess up the missing values, right? So I'll say else if alcohol is greater than 1, So greater than 1, where's it greater than 1? no, alcohol, greater than one. Put it right here. Greater than one. And I think this is what I do. And alcohol less than, and what did it go to? Let's see, look at those results. I think alcohol went to 7. And let's take a look at the code sheet again. Yeah, 7. So let's do that. And again, I might be messing up with the code, and there could be more efficient ways of doing this. I can't guarantee that this is the most efficient way, but it's less than. This is what you do, less than or equal, less than or equal, right? Equal to 7. Then alcohol equals 1. Right, and this is probably, we'll find out in a second, right? Life teaches you right away if you make a mistake. Okay. Else. And I may not need to do this at all because I might just do it anyway. All equal to system missing, right? So let's see. And then hit run. All right, let's try this and see what happens, all right? They say trial and error equals trial and success. So let's take a look at this and see if it worked. And it'll tell me right away if I made an error. Let's look under the log. No errors, some nodes. It says format. Oh, yeah, I don't care about those variables right now. All right, so we have these. Oh, yeah, look at that. 0, 1, 0, 1. Woohoo. Nice. Worked. Yeah. 0, 1, 0, 1. There you go. So that worked. All right, so you need to do this then, because now you can go ahead and run this, because now you have a new variable, a new way of looking at alcohol. So our new data set, though, if we just do a proc contents for our data set, we'll only have two variables in it, right? Proc contents equals MV stats dot assignment 3. Now, an alternative would have been to create a new variable called binary alcohol, but I didn't feel like doing that. Sometimes you can just recode it, right? So now we have just the two variables here, right? All right, so this is 0 and 1. Perfect. So now you can go ahead and run it the way we decided to run it for. I mean, what I showed you earlier in this lecture. All right, so that's all I have for you today, unless you have some questions. So first I'm going to stop the recording here, and then I'll answer any questions that you may have. So let me just stop the recording. Are you sure?